Our next talk will be by Pierre Berube. Pierre graduated from Polytechnique in Montreal in 1979 and co-founded SAGX Geophysics in 1983. He now is the president of Abitibi Geophysics, which is located in Val d'Or, Quebec. And the title of Pierre's talk is 3D IP, Depth and Definition Successes.
Thank you, Bill, and thank you for inviting me to present this paper on 3D IP. By 3D IP, I mean also resistivity, that includes resistivity. My title slide is quite different from the one you have in your book. That reminds me the time when I graduated, and I started to end-color my contour maps. Imagine if you had to do it for 3D models. That would be very complicated, and that could be even a showstopper for technological advancement. Talking of advancement, why do we innovate in mining exploration, in geophysical mining exploration? Of course, to answer the needs of our clients. They always want us to see deeper, clearer, and cover larger prospective ground for less money, of course. So what we did at Abitibi, that's our mission, in fact, and I will go very fast through that. In time dominium, we developed a transmitter that can deliver 18 kilowatts of very clean power using only a 12 kilowatt motor generator. That's not magic. We developed the patented infinitive loop to look at deeply seated subvertical conductors. Jim McLeod developed for us the ARMID 2 sensor, which is already better than some high-temp squid. And we have the prototype now of the ARMID 3, which is a sensor that is, right now the prototype is as good as a helium low-temp squid. That's a real achievement. And the big thing will be coming in a few years, the borehole ARMID probe, which will be the first really squid quality B-field probe for borehole operations. And in gravity, we are the exclusive service provider of the borehole Gravilux system developed by Syntrex. In resistivity and IP, we developed the all-to-all 3D approach. And what we are going to talk about today is the high-power 3D solution and the OreVision solution for IP. And I'll try to spark your interest with nice case histories, 4 case histories. In magnetics, we are the exclusive service provider also of the brand new drone mag developed by GEM. So, why do we perform 3D IP? Of course, to discover new mineral deposits. But these deposits, being harder and harder to find, we must improve the sensitivity of our tools in order to see deeper and/or through conductive cover. So that means that we are not satisfied of the existing tools. If I look at that model here, which is a very simple synthetic model using the dipole-dipole configuration, you will see that the anomaly produced by that 12.5 meter wide vein is very subtle. In fact, I call it the detection limit of dipole-dipole in this case. And we calculate other models also using pole-dipole and pole-pole, and it's worse and worse. So with an inline array, we feel that there's a limitation in your sensitivity. So we developed the high-power 3D, and before showing you how it works, I will show you the same synthetic model. So we calculated the high-power 3D synthetic response and carried out an inversion, 3D inversion, and I'll show you the profile, the section, the vertical section. Of course, we take so many measurements in all directions, it would not be possible to show you a 3D pseudo section. So this is the inversion. It's a little bit different. It's much better than what you have in your book. In your book, it's from version 3 of high-power 3D. This is from version 5. So there's a really nice correlation between the model and the inversion with high-power 3D as compared with dipole-dipole before. So let's have a little look under the hood. What we do in the field, we lay out up to 48 electrodes. We can lay out more than that if we want, along 5 lines. All the electrodes are connected to a central unit, a electronic switch box that is connected to the receiver. So that makes a total, in this case, of 240 addressable electrodes. The distance between the electrodes can be, depending on the cable you select, 25, 37.5, 50, or 100 meters. That makes a possibility of over 28 different dipole combinations. Of course, we don't want to measure all of them, it would be much too long. We don't want also to proceed as a trial and error to find the best ones. So the way we did it is simply by analyzing the sensitivities. If we take a conventional array like dipole, inline dipole here, it's n equals 6. I will show you the sensitivities at 100 meter depth, a plan view of sensitivities at 100 meter depth. If you run a survey on that line 3 east, and you pass over an ore body, you see that you minimize the intersection between that ore body and the sensitivity volume. The spatial convolution would be at a minimum. So with inline array, usually you carry them almost perpendicular to what you're looking for. So you're always trying to minimize your apparent chargeability response. That's interesting. If, on the other end, you work on many lines, if your 2 dipoles like here are not on the same line, the same sensitivity pattern at minus 100 meter will look like that. And if you encounter an ore body oriented along that direction, the chargeability response will be nearly at a maximum. So because we scan and we will have the transmitter here and the receiver can move from different position. So we will always have a position for which the sensitivity will be at a maximum. Another example of such a combination of 4 electrodes is what we call the original high power 3D, where the receiving dipole is straddling over the current dipole. And in this case also, you see that the sensitivities are really favorable for some direction of some ore bodies. The beauty of that system is that it's quite flexible. It's not hardware fixed, you know. So it can evolve with time. We are now at version 5 commercially available and working on version 6. And we're always looking at new ideas to improve with experience. You know, it's like an expert system. With experience, we learn. At one point in time, we added the Schlumberger array to get to make some soundings and to have a much more higher vertical resolution, especially for the interface between overburden and bedrock. So, and in fact, like for instance, there's a paper that has been published last month showing the benefits of the gamma 11N configuration. You see the sensitivity pattern, vertical section of the sensitivity pattern of that configuration here for n equal 2. Oh, 2, yeah. And we are investigating, we're doing some synthetic model to see if it will be worth including that type of measurements into high power 3D. So it's an evolving system. So the setup usually, as I said, is over 5 lines. We move the transmitter dipole along the central line. Once all the line is read, then we move everything to the next setup on line 4, 5, 6, and 7, and 8 with the 2 line overlap, and the current will be on line 6. With all the measurements we are taking, that makes a total of 210 readings per injection dipole, in comparison with a normal inline dipole, it could be 6, 8, or 10 measurements. So we take a lot of equatorial, quasi-equatorial, high power 3D, Schlumberger sounding, and offset dipole readings. We are trying to get the best of all the readings. That makes a total of 10,000, over 10,000 readings per square kilometers. All that without the need of heavy equipment. So very flexible, very cost affordable. Approximately 5 times less expensive than other 3D IP surveys. And thanks also to some QA/QC software to handle that big number of data, and also to test equipment, laboratory equipment to check and control the quality of the equipment. And even a custom made by Iris, a 15 amp portable transmitter. So let's have a look at 2 case histories. The first one here, unfortunately, is not drilled yet, but it's a really nice one. Probably that once things will get better in the financing, they will drill it. This is in the Gold Corp, in the Red Lake area, just east of the Gold Corp Campbell mine. And our client is Rupert Resources. This is their property, and the favorable trend is passing just on the northern edge of their property. They are very lucky because the dip of that favorable horizon is south. So they expect something at depth to the south here. Now, to investigate deep in that area at the end of the property required that they had the permission from their neighbor to the north, Conquest Resources, so that we could deploy a part of our high-powered 3D array on their property, and Conquest kindly acknowledged. Again, this is the property in red, but what they want to do is simply to survey the northern part, including a part of their neighbor. These are the results of the 3D inversion. That's almost a minimal survey. The property is not very wide at that part, so there's only 8 lines have been surveyed. The bottom color map here is the apparent resistivity, not the apparent, but the 3D inverted resistivity. The cold colors being the resistive zones, and the warm colors here, the conductive zones. This is a known shear zone that has been extensively drilled by Conquest Resources to the north on their property with very low grade values. Okay? But you can appreciate the resolution of the technique down to 700 meters. You could not achieve that with inline results, but with equatorial and other type of results, it's possible. Now, here in green, you have the chargeability, the 55 millivolt per volt chargeability envelope of 2 nice anomalies that looks to be connected together, not necessarily at depth. And the beauty of the thing is that this one is exactly along strike with the favorable horizon that is hitting south. So this one here. The other one is quite intriguing, but it's not drilled yet. The second example has been extensively drilled. That's the B26 zone belonging to SOCWEM, the Société Québécoise d'Exploration Minière, in an area where you get the Dipole Lake mine, the Casa-Berardi mine, the new Balmoral Grasset discovery, northwestern, that's in northwestern Quebec, northeastern Ontario, and that's a place also where All in Blue, Midland junior company from Quebec just raised $14.4 million to prospect in that area. So it's a very hot area right now in Quebec and Ontario. The reason why they ask us to do an high-powered 3D survey, because the zone is already known, they wanted to have a tool, the best tool to investigate and to discover other deposits of the same style. And the difficulty here is that the deposit is located fairly close to a graphitic horizon. So we ran a 41 9-kilometer test of high-power 3D. And this is the result of the 3D inversion, the 3D model. So you can see it, this is the south here, the north, the graphitic horizon very clearly here, and the copper-rich zone, which is conductive also. And you will see, I will see you in 3D. So this is here the mesh from the geological model, That's a two or three old model. They drilled much more last year, and they will issue a new model shortly. The zone, they really continue in that direction. You see that the resolution is fairly good, down to 350 meters, which is very good. We can resolve both zones. Okay, for the resistivity, now we'll have a look at the chargeability. Here, it's a copper zinc deposit. I was showing you only the copper-rich zone, which is conductive. The zinc zone is not conductive. It's even a little bit resistive. And if we look at the chargeability model now, you will see that it will encompass both sulfide zone, the copper and the zinc zone. And again, they drill in that direction because there's a fault here, and they drilled and they still encountering mineralization. So that's for chargeability. Now I told you that the zinc-rich zone was even resistive, so just for the fun, instead of calculating the metal factor, I calculated the zinc index. And it really, not just for the fun of the thing, but it really focus on the zinc zone. I got it again with my thumbs. So, okay. Now on section view, you got the resistivity and chargeability inverted model, 3D model, and there's no way of distinguishing the graphite from the sulfide. You see here that the chargeability is much wider than the resistivity. Same thing in plan view. This is a metal factor, sulfides and graphite here, two similar geophysical response. But if we do some spectral processing, then we can distinguish graphite from sulfide. And that's really promising. We got a lot of samples from the client to double check that in the lab, to have really the confidence that we could, from field results, distinguish both signature, even if they are even closer than what they are here. So conclusions on the first part of that talk on high-power 3D. Conventional IP inline configuration have a shallow depth of investigation, especially to conductive overburden. High-power 3D will maximize the sensitivities yielding enhanced response, and also maximize the vertical and horizontal resolution of target mineralization, and provides accurate diamond drill hole targets. Now, during these tough days, it's not all the clients who really want a more expensive type of survey. So the projects that get financing right now are the most advanced project, where you already have some mineralization, and when you're sometimes looking deeper. So people don't want to pay too much, they don't want to pay much more than they are paying right now for a survey, but they want to see deeper. So we had the idea of using all the technology, all the hardware and the software we developed for high-power 3D to simply push the dipole to its limit. So measure up to n equal 20 or 30 using almost the conventional dipole. So that makes a cheaper solution to see deeper. So we want to keep the near surface resolution while maximizing the depth of investigation, all that to a cost of a conventional IP, almost the cost of a similar conventional IP survey. And as a bonus, if the price is right, we could carry out a 3D inversion if the line interval is not too large. So the setup in the field is much simpler than the other one. We lay out the same cable with the switch box and the receiver and the transmitter, while the transmitter is moving along the line and the receiver is taking all the measurements down to n equal 30. The second part of the crew will lay out the next line, and as soon as the first line is ready, the transmitter and the receiver switch to the second line. So the receiver is really taking measurements more than 75% of the time, making it possible to offer that type of survey almost at the same price as conventional and equal 8 or 10 survey. So you get much more data for about the same price. First case history, in fact, it's a discovery. Discovery, one of the first OreVision survey led to a discovery it's very close to Val-d'Or, 8 kilometers east of Val-d'Or, along the famous Cadillac Break. So the history is the client had a compilation. They had a prospective trend here, but some of the surveys that were done in the past show very, very low chargeabilities, and in some areas they even stopped the survey because they were not, as they say, penetrating the overburden. So they asked us to do an OreVision survey in that block here. I will zoom a little bit here. And this is the result of the OreVision 3D survey. This is the resistivity inverted at 50 meters, at a depth of 50 meters. You see that area of thick overburden here, much less overburden here. And same thing for the chargeability. Thick overburden, very low chargeabilities, very strong chargeabilities here where the overburden is thinner. Now if we look at minus 150 meters, wow, that's what the historical survey missed, all these zones here. And particularly this one was of interest because even at 300 meters depth, you can see that it's still there and even larger, stronger. So we will see now the profile of line 5 east, the section, the inverted 3D section. Well, buttons are really close one to the other. And they drilled the first drill hole, our first priority anomaly we had. The first drill hole they did at the beginning of the summer after our survey during winter. They encountered 150 meters thick of porphyry type of mineralization containing a lot of copper, gold, and molybdenite. It's the first, not only a discovery, but it's the first time in that along the Cadillac Break, which is nearly 200 kilometers long, that this type of mineralization is encountered. The last case history is from a property in the northwest Quebec, also a gold deposit on the Benoist property belonging to Cartier Resources. In fact, it's also an advanced project. They already have a deposit on site on the property, a gold deposit. Too small to be mined. They are looking for the same type of deposits. So the VP Exploration has shown me some mineralized core samples and asked me what I would do to detect similar deposits on the same property. So I told him that it looks like IP should be the good tool to use, but he said, okay, prove it to me. So a good thing about the downturn in exploration right now is that geologists and geophysicists have the time to talk, and we have the time to look at samples, we have the time to do some testing. So what we did first, the first step, we make some physical property measurements on with the samples they gave us. And it clearly shows that the mineralized sample had a small resistivity contrast, a decrease in resistivity, and an increase in chargeability. So we said, okay, it's promising. That was step one. Step two is really to do a test line. It's not because it's responding in the lab that it will respond in the field. The deposit may be too small, may be located under a very thick layer of conductive overburden or any other challenge. So, and we wanted to test also for them a new technology, a new array, the OreVision array. So, and it was over a lake. We ran a 2 kilometer long test line. And all the graphics you will see are from the Cartier website. You know, these graphics have all been done by Cartier Resources. They were quite pleased with all the results. And you see here the deposit. The deposit in fact is plunging to the southeast. So the top of the deposit is here, and the bottom at something like 400 meters is here. So where we did the test is where the deposit is at 150 meters. And the apparent dip to the north here is not true. The deposit is vertical. This is only one line to the inversion, and the effect of that dip is due to the upper part of the body here, which is to the north. So that tends to draw the body to the north. So with these promising results, they decided to cover all the prospective area over the lake, because that was during winter. Again, that's a figure from Cartier Resources. So that's our chargeability, 3D chargeability inverted at 300 meters with the Pusticamica deposit here. And they are quite interested at everything that is along these channels, these structures, intersection of these structures. The black boxes here, rectangles, are all drill targets that they will drill. On the cross section here, you see on line 750 west, the upper part of the Pusticamica gold deposit here. Again, it's like a cigar that is plunging in the plain on the other side of the screen. And so we had another response here at depth, another one here. This one is different. This is not the same source, because this is plunging to the west. So conclusion on OreVision this time: excellent depth of exploration, the maximum we can get from dipole-dipole. We retain near surface resolution. Some people will, maybe that's a question some people will ask, so I will wait about the resolution and the spacing. Good data quality, absolutely mandatory for a good 3D inversion. And as I said again, we can invert in 2D if we get enough line or small enough spacing between the lines to avoid lateral effects. If you do that type of survey, because that type of survey is quite similar to the Titan survey, except instead of being pole-dipole, dipole-pole, it's dipole-dipole simply directly. And but the fact that it's kind of 5 times less expensive, or even more than that, you can run it on every line, every 100 or 200 meters. The problem is that if it's very expensive, the client will do a survey, a line every 500 meters, for instance. And if they have a source in between 2 lines, you carry out to do inversion, you will have a source, a target on your 2D section. You will drill it, you will miss it, because there's nothing. It's in between the lines. So that's important to have a fairly close coverage. If it's too expensive, that's nice, make a lot of money, but your client won't have success. And I think that's all. Yeah, thanks to those who allowed us to publish these results. Thank you.
So there's a few minutes. If there's any questions?
Have you tested this technology on any carling style?
Absolutely not. We want to. We're waiting simply. We have a lot of job to do in Canada and in some other countries also, but we would like to test it for sure. It will be interesting. Yes?
Can you define your frequency dependence inversion?
Oh, it's we use the software developed by the Australian Geophysical Research Group. It's a software that allows you to invert the cold pole model in time domain without fixing the frequency parameter. So the normal inversion you see you have with Geosoft or with the instruments, they fix the frequency parameter to say something like 0.25, the exponent in the equation, and they let the time constant be inverted. In our case, we have an inversion that let both parameters free. You have to set, of course, some initial parameters, but that gives you a more knowledgeable, I think more acceptable cold pole inversion. But right now we are working on something completely different than cold pole. We are not satisfied with cold pole. The cold pole model is can model almost everything that is decreasing. it's not my first choice to do spectral IP. We are working on something else now. And with the OreVision, we have the same spacing, even if we are going deeper. And I know some people say start at 25 meters, then go to 50, then to 100 meters to go deeper. Because, of course, you have less resolution at depth, though, so it's not necessary to have a smaller spacing, a dipole that is as small at depth than at surface. But in our case, it's the same price. We do it anyways. And if at larger spacing we have some noise, instead of losing 1 or 2 readings at 100 meter interval, then you're losing 200 or 200 meeting of data. If we are losing one data, we have a lot of others. So that's very good for the inversion. And again, that doesn't cost much. And it's the same, it's not a signal to noise question, because it's exactly the same signal to noise. You increase your spacing, you increase your primary voltage, but you're increasing also your televic signal. Sorry.
Okay, thank you very much.